start the recording. Looks good. All right. Topology. So last week we finally got our definition of what these things are, a topology. It's a very intuitive definition, right? You could have almost guessed it. No, nothing intuitive about it. So what is a topology? Let's remind ourselves. Let X be a set, and let tau be a collection of subsets of X. So what's in tau? Subsets of X. Now, tau is a collection of subsets of X satisfying these three properties. If it satisfies these three properties, it is a topology on X. So what makes a topology? First off, the empty set has to be in tau, and the entire set X, that's big X, has to be in tau. That's the first thing it has to satisfy. Or in other words, the empty set and the entire set have to be open sets. Open set was our way of saying it's in the topology. When we say a set is open, that means it's a member of the topology. So the empty set has to be an open set, and the set X has to be an open set. That's property one. Property two it has to satisfy is that for any finite number of open sets you choose, so I've got u1, u2, ... u sub n, where n some finite number. Could have been 10, could have been 20, could have been 100. Pick any finite number of open sets you want. Remember, tau is our collection of open sets. You guys remember that terminology right there? That means in. So we have u sub 1, comma, u sub 2, ... u sub n in tau. If all those sets are in tau, then their intersection better also be in tau. Pictorially, what that means is, if here's X is this space right here, and if this set is an open set, and this set is an open set, and this set is an open set, then their intersection better also be an open set. Otherwise, it's not a topology. Topology has that property. For any finite number of open sets you find, their intersection is also an open set.
You find open set.
Open set just means it's a member of the topology.
Standard with topology.
Yeah, so we're defining what a topology is, and then what do we mean by open set? It's in the topology. But rather than saying in the topology over and over again, we just say is open, is what we're going to eventually get to. So now if you got intuition for that, let's remind ourselves of the notation. And now I'm going to read this precisely from the notation. If u1, that arrow right there means I'm doing an if-then statement. If u1, comma, u2, comma, ... comma, un are in tau, then the intersection from I equals 1 to n of u sub I is also in tau. Or in other words, if we intersect, when we plug in 1, 2, 3, 4, 5, 6, all the way up to n, intersect all those sets, that set better also be in tau. Dense notation. It's just as important that you get the notation as you get what the notation is trying to convey. Because you need dense notation to convey dense ideas. All right, and the third property. The third property said, if we have any arbitrary collection of subsets of it, let's remind ourselves of this. What's the power set of X? Every possible subset. Let's do a concrete example really quick. If I say the power set of the set AB, what is this equal to? A, B, what we spelling? Abracadabra? We're doing some magic here. What's it equal to? The set, what?
A.
The set of A?
Yes. And then the set of B.
And then the set of B? So we're doing, are we ending?
Yes, ending set.
Oh, okay. So you're saying it's equal to the set A, comma, the set B, comma, the set AB.
And that's also a whole set, isn't it?
Yes, all this is in a set. It's the set of sets. There we go. Now you guys have the right idea. Let's rewrite it out correctly this time. So it's equal to the set of all possible subsets. What are all the possible subsets we could have of A, B? We could have the set that contains nothing. That's the empty set. We could have the set that just contains A. We could have the set that just contains B. Or we could have the set that contains AB. All right, there's the power set on AB. So if I were to define a topology on AB, a topology on AB is going to be a set of subsets that satisfy these properties. So let's come up with a topology really quick. One possible topology we could have on this is the empty set and then the entire set itself. We call that the trivial topology, right? This is a potential topology on the set AB. Notice that a topology is always going to be a subset of the power set. Every topology always will be, because topologies are composed of subsets of our initial set. Okay, so let's read what this says now. This says, for any arbitrary collection of subsets of X, if X is an infinite set, this set over here could also be infinite. For any arbitrary collection of subsets of X, their union is also in tau. So what does that mean? Pictorially, let's draw a picture of this. So here's my X. Here's one open set in tau. Here's another open set. Here's another open set. What does property 3 mean? It means the union of all three of those sets has to also be an open set. It means this set is also an open set. The union of them all. So now I'm going to restate this in high-level language. A collection of subsets tau is a topology if it contains both the entire set X and the empty set, if any finite intersection of open sets is an open set, and if any arbitrary union of open sets is an open set. Then it's a topology. Those are the three rules it has to satisfy. And we talked about two special topologies last time. We talked about the trivial topology. The trivial topology is a topology that just contains the empty set and then the entire set X, whatever X is.
Can that be derived from every set?
Every set can have this topology on it. Given a set, there are many possible topologies you could define on that set. There isn't the one topology for a given set. There's many. I can't remember what the number was, but it was something like if you have a 7-element set, then the number of possible topologies was 9 million and something. So there's a lot of possible topologies you can define on a given set.
I'm not understanding how union applies, especially because the trivial topology has no union.
All right, so let's look at this one. Trivial topology doesn't satisfy these three properties. First, property 1. Property 1 says the empty set is always in there and X is always in there. Does it satisfy that? Yes. Property 2 says, pick any finite number of open sets you want. Here's all my open sets in this case. Pick any finite number you want, take their intersection. Is that in there? Well, let's see. I can take that and intersect it with that. What do I get? In the topology. I intersect those two. What do I get? The empty set. I take everything that's in the set containing nothing and everything that's in X. What's in the set containing nothing? Nothing. So any set, say A is any set intersected with the empty set is always and forever equal to the empty set. Kind of like multiplying a number by 0. Any number times 0 is 0. Any set union with the empty set is always equal to just that set. That's kind of like multiplying by 1. We're adding 0, actually. Doesn't change it. Okay, so here's one topology we can make on the set. Here's another topology we can make. It's a pretty stupid topology, pretty useless one, but it's one you can do. What's another one we can do? The power set on X is always a topology on X. The power set, the set of all possible subsets. That's a topology. Let's check it. Is the empty set a subset of X? Yes. Is X itself a subset of X? Yes. So those two are both in the power set of X. All right, let's see. If I take a finite number of subsets of X and I intersect them together, do I get a subset of X? Yes. So any finite intersection of subsets of X is still a subset of X. So it's going to be in the power set of X, which is all possible subsets of X. What about any arbitrary union? If I take a bunch of sets of X, subsets of X, and I union them together, do I still have a subset of X? Yeah, I could have union things inside of X and got something outside of X. So that's another special case of a topology, the discrete topology. All right, another concrete example. Let X be the set A, B, C. Let tau be this set. Question, is tau a topology?
What is tau? That is simple.
This is tau, right here. It's a T with curvy top.
It's just a symbol.
It's a Greek letter, yeah. So is this a topology?
No.
No. Why not? It doesn't have C by itself, right? Why do we need C by itself? Which rule are we breaking if we don't have C by itself?
The one, because A and B, when you union them, there's not a subset of A.
Okay, he's saying we're missing the set A, B in here. Okay, good. What's he thinking? He's thinking any union of open sets has to be an open set. He said, when I union those two together, what do I get? AB. Where's AB? It wasn't in there, so we had to add it. Okay, now we for sure have a topology, right? Let's check our properties. Do we have the empty set? Do we have the entire set X? Yep, right here. Don't be confused just because I didn't reuse the X symbol. Okay, now, if we take any finite intersection, do we get something in that set? What happens when we intersect these two together? You get the empty set, intersect. Intersect means what's in both. If I intersect those together, what do I get? Hey, intersect those together, what do I get? Intersect those together, what do I get? And obviously, if we intersect any of them with the empty set, we get the empty set. So we can intersect the things together. What about unions? What happens if I union those together? Get the second thing A. What happens if I union those together? AB. What happens if I union those together? Union those. Seems like it works. What happens if I union all the sets together? What happens if I intersect all the sets? Empty. We keep getting sets in there. So yes, this is now a topology on this set. It's going to be a long time before you get intuition for these things. So you're just going to have to manually turn through your head, does it satisfy this? Does it satisfy this? Does it satisfy this? There's no trick to getting it. All right. Now let's do a much harder topology. So we're going to be on R. Remember what that fancy R is? It's the real numbers. So the way we visualize that is the real number line. And it's going to be the best way to visualize what that set is. Think about the real number line. Back when you were in 4th grade and they put it on your little desk for you, right? That's the number line we're talking about. All right, so on R, we're going to define a topology. We're going to call R, and then I have a subscript here of FC for finite complement. This is going to be our topology, rather than a tau. So we're on R. We define a topology RFC, whose open sets have a finite complement in R, or the set's empty. So if it's empty, or it has a finite complement, it's in our topology. All right, what on earth is a complement, and then what's a finite complement? The complement of the set is everything that's not in the set. The complement of a set is everything that's not in the set. So if we're on the real numbers R, the real number line, and I look at the set 1, how many points are in that set? Just 1, right? Not talking about topology right now. Just saying, here's R, here's a set containing the number 1. Good so far? How many things are in that set? 1 thing's in that set, which is a finite number, right? What's the complement of that thing? Everything that's not 1. If you were to draw that on a real number line, what would that look like? Here's 0, here's 1, Here's 2. That would be everything, except for at 1 we'd have a hole. And then everything else going off to infinity in both directions. That's the complement of 1 on the real number line. So if I let U, the set U, equal R minus the set containing 1, what is U? U, it's the set I have drawn right here. This is U. It's everything except 1. We took all the real numbers and we got rid of 1. So here's U. What's the complement of U? What's everything that's not U? 1. So U has a finite complement. Its complement is just a set containing 1. On the other hand, let's say that we were talking about the real number line, all the numbers starting at 0 going down this way. What's its complement? All the numbers starting at 0, not including 0, going up this way. Is that finite? So this set does not have a finite complement. We're talking about the subsets of R that have a finite complement. What's your question?
I'm wondering if you can define these sets in interval notation.
One like this?
Yeah, so like negative infinity to 1.
We could have just as easily called it U is equal, sorry, I was thinking union when I wrote U. U is equal to all the numbers from negative infinity, comma 1, union all the numbers from 1 to infinity. So yes, we could have written it that way, but that's very tedious, especially if I want to do the set R, but we'll get rid of the points 1, 2, and 7. Yeah. Now I don't want to write out all those unions in interval notation. So let's look at this set. What is U? Right, so here's 0. We have a hole 1, 2, 3, 4, 5, 6, 7. We have a hole here, we have a hole here, and we have a hole here, but we have every other point. So here's our set U. All the points that aren't 1, 2, or 7. What's the complement of U? The set containing 1, 2, 7. Is this set finite? So U has a finite complement. So U is in our topology. Our topology is a set of all sets that have a finite complement, together with the empty set. We have to specially say the empty set because what's the complement of the empty set? All the real numbers. Is all real numbers finite? No. So our finite complement topology is the empty set together with every set that has a finite complement. And the way we write them out is R minus, and then we write out the finite number of items that we're removing from our set. So that's how we write them out. Go ahead.
Can U be finite as well and have a finite complement, or does it have to go to some sort of infinity?
It has to go to some sort of infinity. Because, let's do this by way of example. Let's say that U is equal to A minus B. We know that A is finite, and we know that B is finite. Well, if I have a finite set and I remove a finite number of elements, I'm left with a finite number. And so U would have to be finite.
So U can be finite.
That would make U finite. But is U finite? No, it's infinite. Oh, you were saying it the other way.
Yes.
Okay. Can I start with an infinite set, remove a finite number, and be left with a finite number? So this is infinite. If I take infinity and I minus a number, am I left with a number or am I left with infinity?
You're left with infinity.
You're left with
So
infinity.
what if you take something like naturals? Is there some way you could play with it where you could be...
The naturals aren't finite. If you take away the naturals, then now your complement is no longer finite. It's infinite because the naturals are infinite.
Okay, I see.
And so in that case, you have an infinite minus an infinity still gives you an infinity.
Yeah.
But they're different types of infinities. And the statement I just made was a bad statement. But it gives you the right intuition. Because we can't do infinity minus infinity. Talking nonsense. Okay. So that gives you an idea of some of the things, or that gives you an idea of this topology. You need to get intuition for this topology, because as pointless as it sounds, as random as it sounds, it's going to be an example that we come to over and over again in the class. It's a common example of a topology we're going to talk about. So I want to make sure you completely understand it. On R, we define a topology, R of FC, the finite complement topology, whose open sets have a finite complement in R, or are the empty set. Go ahead.
Wouldn't that mean all the elements in the finite complement? Wouldn't all those sets be infinite then?
Every single one of them is infinite, with the exception of the empty set.
Okay, I'm understanding it
If we're on R. So in this case, yes. Okay. So an example of one of the sets, U equal to R minus, we get rid of the point 0, pi and root 2 over 2. It's going to be the real number line with a hole at 0, a hole at root 2 over 2, and a hole at pi. Got it? So there's our topology. Let's actually prove that this thing is a topology. Okay? So, first thing we need to prove is that the empty set and X are in topology. Now, let's just walk through the logic of this first. Is the empty set in the topology? How do you know? By definition, we says, or we're the empty set. That's always included. Okay, is the entire set R in the topology?
Yes.
How do you know?
I can't see it, but I believe it's in the definition.
It's not in the definition. Yeah, what's the complement of R? The empty set. Is the empty set finite? Yeah, it's got 0 elements in there. It's about as finite gets. So, observe that the empty set is in R sub FC, sorry, curving up, by def, comma, and that R equal to R minus the empty set as a finite complement. Which gives me that R is in, sorry, that's an in symbol, is in R sub FC. Okay, so we know that the empty set is in there, and we know that R is in there. Cool. Step 2, what do we need to show?
That satisfies the condition of the topology.
Well, we just made sure it satisfies condition 1.
Yeah.
Now we need to show it satisfies condition 2. What is condition 2? Tell me in high-level language what condition 2 says. Perfect. The intersection of a finite number of open sets is an open set. That's what we need to show. So what do I need to do? I need to grab some finite number of open sets out of there, some random collection of open sets out of there that's finite, intersect them together, and see if I get an open set. Yeah, how am I going to do that? Well, we'll just try it. So first, let's grab them. Let U1, comma, U2, comma, dot, 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 comma, U sub n be in our topology. So I grab some finite number. How many? 17, right? No, it's 18. No, it's just a finite number n. We don't know how many. We just grab some arbitrary number. We just know it's a finite number. And this is the one that's just missing the point 0, and this is the one that's just missing the point 1, right? No, I don't know anything about them. I just know that they're in there. That's all I know about them. Which points are they missing? I don't know. But I know that they're only missing a finite number. Each of them has a finite complement, or they're the empty set. Right? All I know is that they're in this set. So let those be in there, and observe that if any u sub I, or in other words, if u sub 1 or u sub 2 or dot, 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 when we refer to an arbitrary one of those, we're going to say u sub I. if any u sub I is equal to the empty set, then the intersection of all those sets is going to be, it's going to be the empty set. If I take the intersection of a bunch of sets and one of them is empty, the entire intersection is empty. It's like if I ask you to do this in your head really quick. I want you to tell me what's 17 times 9 times 0 times 91 times pi over 2 times 2. What's it equal to? Oh, that's some crazy fast math. 0 times anything is 0. Anything intersected with the empty set? Empty set. So if any of those are the empty set, then the entire intersection from I equals 1 to n of u sub I is equal to the empty set is in our topology. We already know that. So that is if any of them are equal to the empty set. Now what if none of them are equal to the empty set? Is it still in our topology? We have to show that. So 3. Assume no u sub I is equal to the empty set. Is that okay how I wrote that?
Assume.
Oh, that's not what I meant by is that okay, but assume for all u sub I, comma, u sub I is not equal to the empty set. So let's assume none of them are the empty set now. We know if one of them are the empty set, it's in the topology. What if none of them are the empty set? Is their intersection still in the topology? That's what we need to show. Now, if none of them are the empty set, what do I know about them?
They go to infinity.
There's an infinite number of elements in there. We know that. What else do we know about them?
Each one can be rewritten as a set of real numbers.
They each have a finite complement. So assume for all u sub I is not equal to 0. What does that give me? That gives me that for each u sub I, comma, there exists, backwards capital E means there exists f sub I such that u sub I is equal to r minus f sub I, where f sub I is what? Start with an F. Finite, where f sub I is finite. So I know that each of these u sub i's can be rewritten as r minus some finite set, because they're in the topology. And remember, every member of our topology either has a finite complement or they're the empty set. We already made sure that none of these were the empty set. We already handled the case where one of them's the empty set. So now we're handling the case where none of them's the empty set. Because if any of them were the empty set, that's handled here. And we showed they're in the topology. If none of them are the empty set, then every single one of them has a finite complement. So each set can be written as R minus its finite complement. You take R, remove the complement of the set, and you get the set. I don't know. We all with me so far? We got that? It's dense. Okay, so we know f sub I is finite. Where f sub I is finite. Okay, so now let's look at the intersection of these things. And oh boy, I don't think we went over this yet. Did we go over how the intersection of a difference is equal to a difference of a union? I don't know how to say it.
We did go over the theorems.
Yeah, you guys who missed set theory might miss this, so I'll try and give you a picture of it really quick. So I'm giving you a picture for, well, let me write out what we're going to try and figure out. I'll write it first, and then let you be like, well, how do you know that? And then we'll go over it. All right, so let's do 4. So then we want to look at the intersection of all these sets. So then the intersection from I equals 1 to n of all these u sub i's, when we take all their intersections, that's the same thing as the intersection from I equals 1 to n of r minus f sub I. Because each u sub I can be written as r minus f sub I, where f sub I is some finite set. Which one, we don't know. We just know it's finite, though. So intersecting all those together is the same thing as intersecting all these together. You with me? No? Each open set is the entire set R minus its finite complement. As a concrete example, so U sub 17 might be the set R minus pi 1/2 9,999.97. This right here would be my F sub 17. F sub 17 is one that pairs with U sub 17. And it's going to be finite. If this was an open set, its complement has to be some finite set. So each open set U sub I is equal to R minus some finite set, F sub I. Right? Every single one of them. And so we're just pairing them off together. U sub 1 is the one that goes with F sub 1. U sub 2 is the one that goes with F sub 2. And so for each I, U sub I is the one that goes with F sub I. That making sense? Okay, so now we're going to take the intersection. So the intersection of all those sets is the intersection of all those sets. Each open set is just all the real numbers minus its finite complement. Okay, dense notation. I know. A lot to take in. So we good here?
Why are you pairing it with that?
I'll show you why. It's the next crazy step. So this is equal to R minus the union from I equals 1 to n of each of those F sub i's. Okay, how on earth did I do that? That should be the holy crap, what did he just do moment. We'll come back to the holy crap, what did he just do moment. But let's take for granted that, okay, I can make this make sense to you. Notice, if I could go from here to here, what is this? This is R minus a union of finite sets. If I take a finite union of finite sets, what am I left with? A finite set. And so R minus a finite set is an open set. And so if I can make that click in your head, then you can see how this whole set now is in our topology. That is in R sub FC. If I can make this step make sense, right? So let's make this step make sense and see what I'm doing there. So first off, let's do it pictorially. Let's say, here's what I'm saying in writing with sets in general. So sets in general. We're not talking about this for a second. We'll come back to this. With sets in general. If I have the set A minus B, and I intersect that with A minus C, and I intersect that with the set A minus D, dot, 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 doesn't matter how many times you do it, we'll just do it 3 times. I'm saying that this is equal to A minus B union C union D. B union C union D. That's what I'm saying up here. The intersection of R minus F1 intersected with R minus F2, intersected with R minus F3, intersected with dot, 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 intersected with R minus F sub n is equal to R minus the union of all those right-hand sets. So it's the same as this. Let me draw this out in a picture. So let's say that here's my entire set A, because A is acting like R up here. So A is going to be the entire set, and then these are all going to be subsets of A. So B might be this subset. Here's B. Here's C. Here's D. With me? Now, what is A minus B? A minus B is everything in A that's not in B. So that's everything outside of B. So it's like B is punching a hole through A. So we get rid of these points. So I'm not coloring in the points we have, I'm coloring in the points we got rid of. So we have A and we punched out those points. That's what we have when we have A minus B. Now I need to intersect that with A minus C. So I need, what's A minus C? That's everything if I punch out C. And I'm intersecting them together. I need everything that's in A minus B and A minus C. So that's if I punch out the whole B and I punch out the whole C. So up to here, our picture is all the points that aren't colored in. You see that? And then A minus D, that is the same thing. And it's in A but not in D. That means we punch out D. And so what did we do? We took A and we removed everything that was in B or in C or in D. Make sense? Okay. And then one more time for those of you who want to see it through the logic of it. So logically, what is this saying? What are all these points? These are all the points x in A and x is not in B. And from here we know x is in A and x is not in C. If we were to grab a random point in here, what would we know about it? We know it's in A and it's not in B, and it's in A and it's not in C. Sure, doesn't matter. And is associative. So the parentheses don't matter. Just like when you're adding up numbers, parentheses don't matter. So everything in A or x is in A and x is not in B, and x is in A and x is not in C. That is a not in. And x is in A and x is not in D. Okay, this is redundant, saying x is in A and x is in A and x is in A. We can write that as just x is in A. So that's x is in A, and we'll put parentheses around all the not ones, just to help us think about, and x is not in B, and x is not in C, and x is not in D, right? And then from those of you from logic, how do we factor a not out of an and?
You take the not out and then change the operations.
Yeah, you swap the ands to ors and factor out a not. Those of you with programming, you can do the same thing. You ever anding a bunch of conditions and you want to think about, oh, now I want to negate this thing? You switch them all to ors. And that's how you pull your not out. Okay, anyways, so this is the same thing as x is in A and not x is in B or x is in C or x is in D. And then obviously that was how we defined the union, right? And this is how we define subtraction. So that gives us A minus B union C union D. I know that's not full proof, but hopefully for those of you who are here with when we were proving with sets, you can see how you would prove it. And then for those of you even more familiar with proof, obviously you'd prove this inductively.
Why would you do it?
Because we just proved it for the case where we're subtracting 3 sets.
Oh.
What if we were doing 4? What if we were doing 5? Does the principle hold if you do 27 sets? I just proved it for 3. So you'd have to do a proof by induction to show it in general. Those of you who don't know what proof by induction is, you're going to hate me when you do know it. And then down the road, when you master it, you're going to love me every time it comes up. Because all things considered, it's a very easy way to prove. But even an easy way to prove is really hard to learn the first time you learn it. Okay. So that's how we get from this step to this step. So the intersection of a bunch of differences, we can factor out that R, and it turns it into a bunch of unions. So we got that the intersection of a finite number of sets is an open set. Crazy. All right. So we showed that if one of the sets is empty, it's in the topology. And we showed that if at least one of the sets is empty, then it's in the topology. And we showed that if none of the sets are empty, then their intersection is still in the topology. So we showed no matter what, the intersection of a finite number of open sets is still an open set. So now we need to do step 3. In high-level language, what does property 3 say?
Union of open sets.
Any arbitrary union of open sets is an open set. It could be a finite number, it could be an infinite number, doesn't matter. Make sense? All right, so let use of alpha be any, we won't bother with arbitrary, be any collection of open sets. Let's think. How do we want to do this?
Well, first, don't you have to prove that the union with the empty set is just that set?
Yeah, so we need to handle the case where all of them are the empty set. So 6. If every set in our arbitrary collection is the empty set, comma, then the union of our arbitrary collection is equal to what? The empty set. If all the sets are the empty set, union them all up, and what do we get? The empty set. And we already know that the empty set is in our topology. So we handled the case where all of them are the empty set. Now let's handle the case where at least one of them isn't the empty set. Then assume there exists u sub, I don't know, we'll call it u sub I, in our arbitrary collection, such that u sub I is not equal to the empty set. If u sub I is an open set, and it's not the empty set, what do we know about u sub I?
As a finite complement.
As a finite complement. There must exist some f sub I. That means that there must exist some f sub I such that u sub I is equal to r minus f sub I, where f sub I is finite. All right, not sure how I'm going to write this next part yet, but let me explain it in high-level language. The concept is clear, but I don't want to get too wordy. So one of these sets is missing at most a finite number of points. Right? This set u sub I, it's one of the sets in our arbitrary collection. So we have an arbitrary collection of a bunch of sets that we're going to union together. Here's one of them. And it is at most missing a finite number of points. Right? Let's pretend it's 10. So it's missing 10 points. If I union it with another set, how many points is it missing? At most 10. It could be missing 9 or 8 or 7 or 6 or 5 or 4 or 3 or 2 or 1 or 0. But it's missing at most 10. You with me?
No. What about the points on the other set that you're union with?
Just talking about this one set for a second. So this one set u sub I, what do we know about it? It has a finite complement.
Okay. Okay.
So this one set is it's just one of the sets in our arbitrary collection. We picked one that we know for sure has a finite complement. Let's pretend for a second its finite complement has size 10. That means it's missing, U is missing 10 points. If I union it with another set, then in their union, how many points is it missing? At most 10. Maybe less, but definitely can't be missing more points. If I union with a set, I can't be missing more points. I have to be missing the same amount of points or less points.
Yeah, I'm confused about that. Why can't you remember?
If I take the set ABC and I union it with the set CBD, could I have possibly made a smaller set? When you union it with the set, you can't get a smaller set. You can only get a bigger set.
Yes.
Correct? Right?
Yeah.
So this set is so massive, it's only missing 10 points.
Okay.
If I union it with another set, could it have gotten any smaller?
No.
No, it could have only gotten bigger. So it could only have more points.
Oh.
So the number of points it's missing could have only gotten smaller.
Because
If we add points to it, then the number of points it's missing must go down. It can't go up. So this set U sub I is already only missing a finite number of points. If I union it with another set, our set could have only gotten bigger, so the number of points it's missing could have only gotten smaller. If I take a finite number and I make it smaller, what am I left with? A finite number. If I take a finite number and I either leave it the same or make it smaller, because that's what we do when we union, right? Maybe I union it with itself. Okay, that didn't change anything. It's still the same size. Maybe I union it with the empty set. Okay, that didn't change anything. It's still the same size. So when I union with a set, I can only make it bigger or stay the same size. Which means the complement of the set can only get smaller or stay the same size. The complement of the set is already finite. If I take a finite number and all I can possibly do is make it smaller, I'm left with a finite number. So if this one set has a finite complement, then when I union it with all the other sets in that arbitrary collection, they could at most be missing a finite number of points. And so the union of all those sets has a finite complement. And so the union of all those sets is in our topology. You follow the thinking there? You see why I don't want to write it, because it was a whole essay explaining. I'm not sure the concise way to say that.
Are you going to write it out for us?
I'm going to say observe that.
Okay.
So 8. Observe that U sub I has a finite complement and that unioning can only make the complement smaller. Complement smaller. Okay. 9. Therefore, the union of all those sets has a finite complement. So therefore, the union of all those sets, U sub alpha, has a finite complement, or is in our topology, is in RFC, which gives me that RFC is a topology. Topology square box. Okay, proved it.
Donnie, that makes intuitive sense to me, but sorry to take so much time.
It's fine.
But
The point is
I'd
to
like
teach.
to flesh it out a bit more. What you're saying is that the union of any arbitrary U sub I plus and another U sub I, correct? Would
U
that
sub I
imply-
is a member of this set.
Yes, I'm saying if you take any two of the arbitrary sets and you union them together, would that imply the union of their finite complements as well? Or am I getting mixed up in that?
No.
Okay, then that makes complete sense.
The finite complement could completely go away.
That's what I was wondering.
Yeah. Typically, as you union sets together, as the unions get bigger, the complement gets smaller. They're inversely related.
So when
As you intersect sets, their complement gets bigger. Because intersecting is making them more and more restricted. And so everything that's not those points is getting bigger and bigger. As the points you're talking about get smaller and smaller. If the points you're talking about gets bigger and bigger, then their complement, or the points that aren't those points, has to get smaller and smaller.
That makes intuitive sense. I'm saying if you union sets together, and that does not imply that their complements are union.
No.
Okay. Then yeah, I caught up with you.
It implies that their complements are intersected.
Thank you. That makes sense to me.
So if you're unioning the sets, you're intersecting the complements. And if you're intersecting the sets, you're unioning the complements. That's dense language. All right, so we did an example of a slightly more complicated topology. And this is one that's never going away. We're going to use this as an example over and over again. So I'm going to say, remember the finite complement topology? And you're going to say, oh yeah, of course. Can't forget it. Okay, what's next? Some definitions. All right. These ones are pretty intuitive. The book has a nice picture. Let's show the picture in the book. All right. Not sure if you can see that very well. These are two topologies on the same set, where all the lines are showing the open sets. Intuitively, which of these topologies is finer and which one's more coarse? This one's finer, this one's more coarse. In general, finer means it's composed of smaller pieces. Coarse means it's composed of bigger pieces. Now, you probably can't tell from there, but all the things that are open sets in here are also open sets in here. We can find all those lines back over here. So they're all included. So all these sets are in this set. Not all these sets are in this set. So these sets are a subset of these sets. This collection of sets is a subset of this collection of sets. So we have two topologies. The coarser topology is a subset of the finer topology. That's what we're about to define. Okay, so if we have two topologies, if tau1 and let tau1 and tau2 be topologies on some set X. If tau1 is a subset of tau2, which one's composed of more pieces? Which one's finer? Tau1 or tau2? Which one has more pieces in it? It's more broken up. Tau2 has more pieces in it. Tau1 has less pieces in it. So tau1 is coarser, tau2 is finer. So we call tau2 finer than tau1, and we call tau1 coarser than tau2. They can be equal. If two sets are equal to each other, we say they're both finer and coarser than each other. Sometimes we want to know if they're finer than each other, but not equal, right? So we have the notion of strictly finer. If tau1 is a strict subset of tau2, so that they can't be equal, then we say that tau1 is strictly coarser than tau2, and we say that tau2 is strictly finer than tau1. So strictly finer means that they can't be equal. Finer means potentially equal. Maybe, maybe not. That makes sense? You got that clicked in your brain? I don't know. For some reason, when I first look at it, for some reason my brain wants to say this one's the finer one. I don't know why, but this one's the finer one.
Well, that kind of makes sense. You get a coarse object and make it finer. Break it up.
Whatever clicks in your head. But this one has more pieces. This one has less pieces. Finer, coarser. Whatever makes it click. All right. Theorem. Let's see what I'm proving now. Oh, I don't know if we mentioned that back over here. I think I skipped this both times. The topological space. I don't think we ever said topological space, which is atrocious. Yeah, I skipped it twice. All right, so we said let X be a set and let tau be a collection of subsets of X such that these three properties are satisfied. Then we call tau a topology, and we call the ordered pair X comma tau a topological space. So a topological space is a set together with its topology in an ordered pair. For those of you from discrete math, you might remember we talked about a sample space. That was the set of outcomes together with a probability function, something that gave it structure. It's a common thing we do in math over and over again. We do an ordered pair with a set and something that gives a set some structure. So here we have a set together with a topology. The topology somehow talks about some structure on the set. Common thing we do. Okay, so that's called a topological space. Topological space, just a set together with its topology, all wrapped up in a nice package. So now the theorem. Let X tau be a topological space, or in other words, let tau be a topology on X. Same thing. Let X tau be a topological space, and let A be any subset of X. Go ahead.
I think you skipped your second definition. Or did you go over it?
I skipped it. Thank you. Because it also uses a topological space. Sorry if you can't read this. I wrote it really big because this part of the whiteboard was so dead. Hope that writing it big will make you be able to read it. So let X tau be a topological space, and that's let. We don't need that in there anymore. And let little x be an element of big X. Then any open set U sub X containing X is called a neighborhood of X.
Okay.
Let's go back to over here. This is a neighborhood of A. This is a neighborhood of B. This is a neighborhood of A. This is a neighborhood of B. Any open set that contains that element is a neighborhood of that element. So when I say, let's look at the neighborhood of A, or let's look at a neighborhood of A, you know two things. You know I'm talking about an open set, and you know that open set contains A as an element. So when I say, let's look at a neighborhood of A, if this were our topology, I could potentially be talking about that set, I could potentially be talking about that set, I could potentially be talking about that set, but those are the only neighborhoods of A in this topology. So when we just want an arbitrary neighborhood of A, we use U sub A. If I want an arbitrary neighborhood of X, I'm going to use U sub X. That's going to be common practice. When you see U sub X, that means... can you see my shot?
Yes.
Okay. All right, we want to go past that. I'm going to write U with some subscripts a few different ways. Hopefully, most of the time you can get it from context what I mean, but in case you can't, let's get some examples really quick. U sub n means we're counting up to and terminating at the nth one. So I usually only use that if we had U sub 1, U sub 2, dot, 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 all the way up to U sub n. U sub I, we only use if we already use U sub n, and U sub I is one of the elements going from 1, dot, 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 all the way up to n. That's typically when we use U sub I. U sub alpha, we use when it's completely arbitrary. There's no ordering to these things. There's no listing of these things. It's just completely arbitrary. U sub alpha, nothing about it. And then when you see U sub x, and unfortunately, sometimes my x's and alpha look a lot alike, I'll only use that when I'm talking about U is the neighborhood of x. So those will be 4 common patterns I use. Hopefully, most of the time it's very clear from context, but maybe it'd be nice to have it explicitly said a couple times. So there's me explicitly saying it once.
I get an example of the topological. That's like what it would look like.
A topological space.
Yeah, what would that look like? An example.
I don't have enough space to write it here, but I do parenthesis, this, comma, now insert that right there, in parenthesis. Topological space.
So it's just, okay.
It's just an order pair with a set and a topology.
Set of all the elements.
And a topology on that set.
Okay.
Yeah, I don't want to say its topology, because remember, for one set, you could have many topologies.
Sure.
So just a topology. So a set together with a topology on that set, in parentheses, that's what we mean by topological space. Okay. What are we doing now? We talked about neighborhood. Okay, so we're on to this theorem, right? And I'm going to need to prove it over here. Hopefully I can move the camera so that we can see all the way over there. But finish off Blackboard. Keeps on going. I think we're good. Okay. All right, what's our next theorem? Our next theorem says, let X tau be a topological space, and let A be any subset of X. Then A is an open set if and only if. For every, that's for every, for all, for each. Those are three different ways we can read that. For every little x in A, for every point in A, there exists a neighborhood. There exists an open set in tau such that X is in that open set, or in other words, that open set is a neighborhood of X, and that open set is a subset of A. Let me draw pictorially what this means, because this can be a bit dense. So here's big X, our whole space. A is a subset of big X. Here's A, it's these points. I'm saying A is in our topology, if and only if, for any point in A you pick. So we pick this point. For any point in A you pick, I can find some u sub X. So for any point X you pick, I can find some u sub X, where u sub X is an open set containing X, and u sub X is inside of A.
Does it have to be inside of A?
Yes, it has to be a subset of A, and u sub X is a subset of A. If I can do that for every point in A, then A is an open set. And hopefully that's intuitively clear, because we just union up all those sets. So here's a point X, there's u sub X containing it. Let's say A had some other point over here, Y, and it had some u sub Y containing it. That was completely in the set. And here's some point Z, and it had some open set u sub Z containing it, and that was a subset of A. If we did that for every single point in A, we could find some open set entirely in A containing that point. If we did that for every point in A, then A has to be an open set, because it's just a union of all those sets containing all those points. You good with that?
Yeah.
Intuitively? Now let's write it out. Common rule of thumb, when you go to prove something, you want it to feel almost obvious before you even try. Well, sometimes you just have to play with it. But it's nice if you can get it to feel almost obvious before you even try. All right, so let's do the proof of this. So what are we proving? I'm proving that for any subset of X you choose, as long as it satisfies this condition, it will be an open set. So 1, let X tau be a topological space. And let A be any subset of X. Which subset, we have no idea. I need to show two things. I need to show that if A is an open set, then for every element in A, we can find an open set containing that point, such that the open set is also a subset of A. So I need to show that if A is an open set, then this is true. And then I need to show that if this is true, then A is an open set. It's an if and only if statement. So it goes both ways. Typically, when you go to do an if and only if proof, you write a little arrow like that to show when you're starting and which way you're starting. Doing this way means I'm going to show that the first thing implies the second thing. So I'm going to show that if A is an open set, then this condition is true. And then I'll go the other way. So 2. Assume A is an open set, or is in our topology. 3. Then, for every single point in A, there exists an open set A in tau such that X is in that set, and that set is a subset of A. A is the open set. Pick any point you want in A. I can find an open set containing that point that's also a subset of A. Yeah, I pick A every time. You pick the point 1 in A. I say, yep, A is the set I choose. Is A an open set? Yes. Does it contain the point? Yes. Is it a subset of A? Yes. So I just barely showed that for any point you choose in A, I showed that if A is an open set, then for any point you choose in A, I can find an open set containing that point that's also a subset of A. Okay, should be obvious. It's going to sound complicated until it just clicks and it's going to sound like the most obvious thing you ever heard. Let me say it one more time. Try to make sure it sounds completely obvious. So we said assume A is an open set. I just barely showed that for every X in A you choose, there exists some open set in tau such that X is in that open set, and that open set is a subset of A. And what's the one I showed every time? Just A.
What if you picked something that wasn't A, that wasn't A?
I-
A subset of A.
I just need to find an open set that did it.
So it's irrelevant which set you find.
Yeah. All this says is that we're proving that A is an open set if and only if for every element in A, there exists some open set such that X is in that open set, and that open set is a subset of A.
Okay.
So I did the first way. If A is an open set, that's obviously true. The proof is much more interesting the other way. So now let's prove it the other way. So this time, we're proving this way. So this time we're assuming, oh no, don't be dead here. We're going to assume that for all X in A, for any point in A you choose, there exists some open set U sub X in tau such that X is in U sub X is a subset of A. Then when I union up all those U sub X's, what do I get? I get A. Now, we proved that a while ago with what was called the union lemma. It was a simple proof. It's a very intuitive proof. So the union lemma, that wasn't last class, but the class before, of all the preliminary stuff we went over, I said this is the one thing that's going to come up over and over and over again, the union lemma. It was really easy to prove. I told you, even though it's really easy to prove, it's stupid useful. We use it all the time in this class. So here's a case where we're going to use the union lemma. The union lemma, in short, said that if you have some set, and for any point in that set you choose, you can find a subset of your initial set containing that point, then the union of all your subsets gives you back the initial set. That's what we proved with the union lemma. So 5, then the union of all those U sub x's for each little x in A. That's not U sub alpha, it's not an arbitrary collection now. It's a U sub x for each little x in A, there's an associated set. So the union of every U sub x for each little x in A is equal to A by the union lemma. And we're done.
Do you prove the union lemma and set theory?
No, we proved it as a preliminary stuff for this class. So we did set theory, then we did the preliminary stuff, then we did this class. Most of the preliminary stuff was talking about relations and functions. This was the only proof that came up in the preliminary stuff. I said this is going to keep coming up in topology. We use it all the time.
Gotcha.
Okay. I guess we can say a couple more things. So then the union of those is equal to A by the union lemma. 6. Therefore, A is an open set because it's a union of open sets. That's 2 words. 5. We said the union of a bunch of open sets is A. And so therefore A is an open set because it's a union of open sets. And then I think we're pretty safe to say square box. Any questions on that proof? You feel like I skipped over a piece of logic? Oh, go ahead.
Is there ever a set where subset's not in it?
Is there ever a set where its subset is not in it? A subset, by definition, is in its parent set.
Yes, you said it wasn't an open set if the little x wasn't in it. But is there ever a case? Step 3.
So on step 3. So right here, what did we say on step 3? We said then for any point you choose in A, I can always find an open set containing it. Namely the set A.
Is there ever a case where that's not true?
Is there ever a case where you can find a point in A that's not in A?
I think what he's trying to say is if there is x in A where it doesn't have a neighborhood.
Where it doesn't have a neighborhood?
Yes.
Okay.
He's asking
Yes.
why it's not part of A.
So come over here and say that A is equal to the set containing C, where this is our topology. Is A an open set? No. Look at, what are our open sets? The empty set, the set containing A, the set containing B, the set containing ABC, the set containing AB. Those are open sets. A is a subset of X. Is it an open set? No. So it doesn't satisfy this condition. This says, assume A is an open set, then this will be true. This says, assume this is true, then A will be an open set. So A here, since it's not an open set, doesn't satisfy this proof. This proof says if it's an open set, then it has this property. A is not an open set, so it doesn't have the property. And then what we said is if it has this property, then it's an open set. Does A have the property? Is it true that for every element in A, you can find an open set containing that element that's also a subset of A? No, that's not true.
I'm actually more confused what an open set is.
An open set is a member of the topology. So in the case over here, it's one of these. Let me rewrite this on the camera. We're doing enough discussion that we should be doing this off the camera. So tau is equal to, let's see, our topology is, we have the empty set, the set A, the set B, and the set AB, and the set ABC. So here's the concrete topology we're talking about. And we're talking about it on the set X equal to ABC. Right? And so we said, let's do a slightly more complex version of A. A possible A could have also been the set AC. Right? A is a subset of X. Now what's this proof say? Huh? So A right now is a subset of X, right? What does our proof say? Our proof says A is an open set, or in other words, A is a member of this topology. Is A a member of our topology? No, so it's not an open set. So this is going to not work with our proof. So this says A is an open set if and only if for every point in A, in this case, it's easy. We have A and C. If for every point in A, we can find an open set containing that point, that's a subset of A. So let's see, starting with this point. Can I find an open set containing this point that's a subset of A? Yes, the set A by itself is an open set. Can I find an open set containing this point? Sure I can. Here's an open set containing that point. Oh, but it's not a subset of A. So that doesn't work. We'll do one where it does here in a sec, but let's make sure it doesn't make sense. So this says A is an open set if and only if for each element in there, you can find an open set containing that element. That's also a subset of A. We can do that for little a, but for little c, we can't do that. Little c does not have an open set containing it. That is also a subset of A. So A is not an open set. All right, let's do one where the proof would work. If we want one where the proof would work, we have to let A be an open set. Which one do we want? Well, you all scream AB at once. It's weird, they all canceled out. Can't hear any of them. Okay, so let's say A is equal to the set AB. First off, is it an open set? Then it's going to satisfy this property. For any element in here, you're going to be able to find an open set in our topology containing that element. Let's see, can you find an open set containing A? Yeah, the set AB. You might be thinking, A, don't overthink. Let's just use the set itself. What's the open set containing A? The set AB. What's the open set containing B? That's also a subset of A? The set AB. You could have also used the set B, but why work harder than what you have to? Let's just use the set A. We already know it's open. So if A is an open set, we just already showed that for every element in its set, we can find an open set containing that element that's also a subset of A. Because A is always a subset of itself.
Which means that, of course,
Now let's come at it with the reverse logic. Let's just say that we knew that we had a set that satisfied this property. So maybe we don't notice that AB's in here. But instead we notice, let's see, I have A. Do I have a subset of A containing that? Oh yes, a set A. Okay, we're good there. What about B? I noticed that time I noticed there's an AB. So I notice that that's an open set containing that, that's an open set containing that. They're both subsets of A. And since I found a subset of A for each point, I know that their union has to give me back A. I could have just as easily chosen the open set B here. Their union still gives me back A. So if for every point I can find an open set containing that point who's a subset of A, union them all together, and we get the entire set A, since a union of open sets has to be an open set, its union's an open set. A lot of open sets. Okay. Breathe in the chalk. We finished the proof, right? It was just more explanation on the proof. Do we need more explanation on that proof? Feel free to ask all questions you want. You're not on a timer. You're really going to fall behind. She's my best student, by the way. Go ahead. Now you're going to fail. All right. Any other topology questions?
This theorem is okay. All X is well. So you were giving an example over here where A and
That was for a bad example. So it's the same picture as we have over here. That's just right over here. So you're saying you want to look at the case where A is just containing C. So now we're in bad example. And so it's going to be a bad example both ways. So is A an open set? No. Which means that for each element in the set, we should not be able to find an open set containing just that element. Or sorry, we should not be able to find an open set containing that element that's also a subset of A. And we can't.
that's also a subset. Okay.
That's also a subset of A. An open set containing, for each point we need to find an open set containing that point. That's also a subset of A. If A is not open, you can't do it. If A is open, you can do it. If you can do it, A is open. If you can't do it, A is not open. They're both back and forth relations.
Now, what is this? What's the point of what's this trying to say? That it proving that that set is an open set.
What it gives us is a logically equivalent way of thinking about a set being open. So it gives us a property that open sets have. Now I know that if a set is open, it has this property. Or maybe I'm working with a set and I'm wondering, is it open? If I can show it has this property, I now know it's open. So if I got a set and I know it's open, this is one of the ways I can work with it. I can say it's open, so I know it has this property right here, and so and work with that property, because this gives me some information to work with. On the other hand, maybe I'm tinkering with some set and I'm trying to figure out, is this stupid thing open? I could check this property for it.
Okay, so and in a way that sounds like a quicker way of checking than is if you were just to grab that set and check it with every single set in the whole entire.
Right, there's going to be times where we're given arbitrary sets and we have precious little information about them. But maybe somehow I'm able to scrape this information away from it.
And this is assuming that the topology is definitely a valid topology. There's no question about it.
Yes, we are. Let X tau be a topological space.
Right. And so because we know it's a topological space, you can use that logic without having to look at the entire set to know that it's an open set.
Correct.
That's pretty neat. So
Yeah.
it's like an efficiency on computation.
Not an efficiency, an abstraction. It enables us to identify them without knowing very much about it. That's what an abstraction lets you do. If I give you an array of objects, you don't know what's in it, but you know they're in an array. That's an abstraction. It's not an efficiency thing. It gives you information about it. You now know it has a count, for example. You know it's ordered. I say, what order is it in? You don't know, but it's ordered. You know that.
Yeah.
So it's an abstraction. If you have an open set, it has these properties. It has its size property. It has the fact that it's ordered. It has these properties.
That's a better way of saying abstraction.
Okay. Anything else on those? You back already?
Yeah, went faster than I thought.
All right. Didn't even notice you come in.
Okay, so we got that theorem, and then this other one, is this the same thing?
This is just proving that theorem. That's where I had it written, and then I proved it over here.
Okay.
And then this was just writing out a concrete example. So, on to the next thing we're proving. Hopefully we can do it, right? Let X tau be a topological space. Then, tau is equal to the power set of X. What's the name of that topology? The discrete topology. Then tau is equal to the set of all possible subsets, if and only if, for every little x and big X, little x by itself is in tau. Let's give you concrete what that's saying. This one's actually easier to get than the other one, even though it might sound harder. Let's say I've got some set here. Not A, X. X is equal to the set A, B, C, D. I say I want you to figure out what tau is. I tell you, this is a topology, but I'm not going to tell you everything about it. I'm just going to give you some special information about it. So you know it's a topology, but the only thing I'm going to tell you is actually in there is the set containing A, the set containing B, the set containing C, and the set containing D. And it contains other things in here, but that's a mystery. I'm going to make you figure out what else is in here. So I tell you, this is a topology. You know it's a topology. And I tell you, these are the only sets I'm going to tell you are in there. What else do you know about this topology? Well, first off, you know it has to have the empty set in there because it's a topology. So I didn't tell you that, but you know because it's a topology, the empty set has to be in there. What else has to be in there? The set A, B, C, D. Probably should have picked a smaller set. We're in trouble. We'll go around to the next line. What else has to be in there? The set A, B, right? Because if that's in there and that's in there, their union has to be in there. So AB has to be in there. What else? CB. What else? AC. What else? What's that? CD. You have to write out all 16 of these? Yeah, there's going to be 16. I could do 2 to the 4 really quick. What else is in there? 80.
Can we just skip ahead?
Yeah, I'd sure love you to skip ahead. What's going to be in there? Every possible subset is going to be in there, right? Because I can create every possible subset now by unioning these things together. The only one I couldn't have created by unioning these things together is the empty set. But we know the empty set's in there because it's a topology. So the empty set's in there, so we got that. And then any other subset of X is going to be a union of some of its elements.
I'm a little confused. I get that the power set of ABCD is in fact a topology, and that you don't have to have every single subset of ABCD for it to be a topology.
Right, two topologies. Here's one topology on X, here's another topology on X.
So, okay, so there's multiple different topologies.
Yep. Here's another topology on X.
Wait, what?
Called the trivial topology. We'll call it tau 1, tau 2. There's two topologies on X. X is a set A, B, C, D in this example. Yeah, sorry, probably should have written it out. All right. So now that we've said that, I think the proof will sound kind of obvious. Let Xt be a topological space. Then our topology is equal to the power set if for any element in X, the set containing that element by itself is in the topology. Because if each individual element by itself is in the topology, then I can just union up combinations of those elements to get every possible subset. Just like we had right here. For each element in there, we knew we had that in our topology. Now to get any other subset of X, I can just union those things together. And since the union of any collection of sets is an open set, they all have to be in there.
In order to prove that, do you use the theorem we just proved?
I don't know. I don't know how I'm going to prove it until I prove it. So let's start with 1. Let X tau be a topological space. Okay, so let's start with this direction, whatever that is. This direction is, if our topology is equal to the power set, then it has this property. So let's do that way first. Remember, I'm showing first this implies this, and then I'm going to show this implies this. That's what we mean by if and only if. Now, for those of you who miss logic, something you're going to hear me say a billion times, how do we prove an implication? We assume the antecedent and show that implies the conclusion. The antecedent is on the left-hand side of an implication. The conclusion is on the right. So, assume the antecedent. So, let or assume, well, since I said assume out loud, I'll do assume here. It just has a lot more letters. Assume tau is equal to the power set of X. And observe good enough. And observe that for all little x in big X, comma, little x by itself is a subset of big X. Is that true?
Yes.
For every element in big X, that set containing that element by itself is a subset of big X? That's always true. If I grab an element out of big X and I put it in a set, it's a subset of big X? Every time? Yeah, if that doesn't sound stupid obvious, we need to explain something. We got some set X equal to like ABC. If I grab something out of there, A, and I put it in its own set, is that going to be a subset of big X? Every time. So for every little x in big X, for each of those elements, put it in a set by itself, and it's going to be a subset of the whole set. Doesn't sound stupid obvious. I need to say it a different way. Sound stupid obvious? Okay. Okay, so, and observe that for any little x you choose in big X, or for every little x in big X, that set containing little x by itself is a subset of big X. Which gives me that that set by itself is in the power set. Because what is the power set of big X? It's all its possible subsets. So if that's a subset of big X, it has to be in the power set. Which gives me that the set by itself, little x, is in what? No, it's not in big X. This set is not in big X. Let's make that very clear. So if big X is our set ABC, is the set containing A in there? No, none of those are the set containing A. That's A, that's B, that's C. It's a subset of it. It's not in there. It's very easy to get confused by those two. So the set containing X is in what? Our topology. Okay. So we just barely showed that if our topology is equal to the power set, then for every little x in big X, for every point in big X, the set containing that point by itself is also in our topology. Now we need to prove it the other way. We need to show that if this is the case, then this is the case. We need to show that this implies this. So we're proving it this way now. For 3. How do we prove an implication? Assume the antecedent and show that implies a conclusion. Assume the antecedent, show that implies a conclusion. So now I'm going to assume that for every little x in big X, the set containing just little x is in our topology. So assume. And soon I'll start writing let instead. Assume that for all little x in big X, comma, the set containing little x by itself is in our topology. That's like what I started with. I showed you an example of. I said we had some mystery topology that had the set just containing A, just containing B, just containing C, just containing D. And we showed that that mystery topology turned out to be the power set. Now we're doing that in a more general way. But we're going to go through the same thinking. So assume that for every little x, that element is in our topology. What am I trying to show? I'm trying to show that our topology is the power set. Right? So I'm trying to show that any subset of x you choose, it's in our topology. I'm trying to show every subset's in our topology. That's the same thing as showing any subsets in our topology. You can pick any subset you want of x, and I can show you it's in the topology. So you got to take some mystery subset of x. So here's your mystery subset of x. 4. Let A be our mystery subset of x. We don't know anything about A. All we know is it's a subset of x. I'm going to show you that A is in fact in our topology. 5. Observe that, I'm not sure how I'm going to write this in notation yet, but I'm going to say out loud what I'm going to tell you. A is equal to the union of all of its elements. A is equal to the union of all of its elements. Take all of its elements, union them together, that's A. So, observe that A is equal to the union of little x for each little x in A. That time I write it. A is equal to the union of all the little x's where little x is an element in A. Now, that means that A is a union of a bunch of open sets. So that gives me A is a union of open sets. Because each of those sets is open. And we union them all together to get A. And if A is a union of open sets, what does that give me?
A is open.
A is open. Which is the same thing as saying A is in our topology. Right? So what did I just show you? I showed you that for any mystery subset of x you choose, I can show you it's actually an open set.
So is X in our topology?
So we have big X, which is a set we're creating a topology on. Oh, is an entire set big X in our topology? Yes, it is. So imagine that you, well, we just barely showed that. Is big X a subset of big X? So this mystery A could have been big X, right? Let's follow through that thought process. Let's say that, so I don't know what this mystery set is. I'm telling you, for whatever mystery set you grabbed, just follow this and you'll see how it's open. So let's say the mystery set that you grabbed was the entire set X. What does this line say? It says that observe that the entire set X is equal to the union of all its individual elements for every element in big X. And since each of those individual elements is an open set, then their union has to be an open set. So your mystery set, in this case big X, is a union of open sets. That means that your mystery set, in this case big X, is open. That gives me that your mystery set is in tau. 6. Therefore what? So I just barely showed you that every subset of X is in our topology. So what's our topology? The power set. Therefore tau is equal to the power set of X. Because I showed you that every single possible subset you choose is in there. But yeah, we also knew the case of big X just because it was a topology. I think we said we didn't know that. We didn't know that. But it also worked here. So sorry about that. Because we started out with let X tau be a topology. So we know tau is a topology. The only question is, was it the discrete topology? That's what we were checking. So I showed if it's a topology that has this property, then it's a discrete topology. And if it's a discrete topology, then it has this property. That's what we showed. Go ahead.
What was the point of this proof? It seems very obvious that
It seems
what
very.
What are you trying to show doing this?
So actually, this right here was actually just a homework problem. So it's not a theorem in the book building up on something. So this was the last theorem in the section, and I picked a couple homework problems to do just to get you more comfortable with all this stuff. So this isn't working towards a big picture goal. This is just help you swallow what we're doing. This was our last actual theorem, right?
Yeah.
Theorem. So I'll specify that theorem versus proof. Proof I'm just doing for the sake of you. Theorems for the sake of pushing the material forward. Good. Glad you asked that, because I'll do that a lot. And I'll just sneak it in there without saying anything. Okay, any other questions on that? All right, let's do our last homework problem. Don't want you guys to have to do homework. That'd be rough. But you guys can just write out the proofs, turn them in next week. They'll be fine. You don't have to. It's a nice little counter. Well, we won't go into that. That's getting into philosophy. I have to move your desk. If you guys are interested in philosophy, we can do it as the next course. We already did it once. Is that so terrible? That's awful. I don't know why. Okay. Next. On a finite set, the discrete topology and finite complement topology are the same. They differ on an infinite set.
I thought you couldn't have a finite complement.
Sure you can. And we're going to show that a finite complement on a finite set is a discrete topology. What does it mean to have a finite complement? It just means your complement is finite. That's what it means to have a finite complement. Right?
Yes, but you have a finite set. Wouldn't the complement of that set be infinite?
No, it's always a complement with respect to set. Remember, complement only makes sense in the context. So if our set X is equal to the set A, B, C, D, then we'll say A is equal to the set A, B. The complement of A is the set containing CD. This is its complement. So complement is always understood in context.
So what do you call X?
And there's a notation I've been hesitant to use, but maybe I can start using it. There's a way that we represent A's complement, and we do A with a line above it like that. Ooh, do we use that for closed sets later on?
Yes.
So maybe we can't introduce that notation. Sugar. Never mind about that. We'll keep writing them out explicitly.
Wouldn't you just say A sub C?
Ooh, is that what we did?
I think that's what we did last time.
I'll have to look ahead in the book. I don't want to start using notation on you and then have it come back to bite. So we'll just keep writing it out explicitly. So what's the complement of A? It's the universe that we're in minus that set. Okay.
Oh, so in reference over here, you were taking the reals.
Yes, over there was the reals. Here, it's just some finite set.
So would the complement of x be x?
Yes. Okay, so 1. Let x be finite, comma, let tau 1 equal the power set on x, comma, and let tau 2 be the finite comp on x. The finite complement topology on x. So we have two topologies here. Our job is to prove that they're actually the same topology. This is a set of all open sets. This is the set of all subsets of x that have a finite complement. And then this is obviously the power set of x. I need to show two sets are equal. How do we show two sets are equal?
You show that they're a subset of each other.
They're subsets of each other. If you know that A is a subset of B, and you know that B is a subset of A, then those two sets must be equal. Kind of like with numbers. If you know that x is less than or equal to y, and you know that y is less than or equal to x, you know that the two numbers are equal. Similar thing here. Now, how do we show that one set is a subset of another? How do I show that A is a subset of B? Show that all the elements in A are in B. Or the way we typically do it is we say, I can show you that for any arbitrary element you choose out of A, that element is also in B. If I can show you that anything you grab out of here is also in here, then this is a subset of this. So that's how we start this. So I'm going to say 2. Let, what should we call our members of T? Probably U. Let U be any arbitrary element in our first topology, T1. So I grab some random thing out of tau 1. I need to show that that's in tau 2. And then later, I may grab some random thing out of tau 2 and show that's in tau 1, and therefore they're equal. That's big picture what we're doing. All right, so I'll let U in tau 1. All right, if U's in tau 1, what do we know?
There's an element in U that's in U, and that implies that U is a subset of tau.
There's a what? There's an element in U.
Is U a set there? Or is
U is an open, oh, I grabbed the wrong, okay. U is in tau 1, which is our power set on X. So U is an arbitrary subset of X.
Thank you. Okay.
That's all we know about U so far. Right?
Arbitrary means random.
Close enough. Unspecified in any way. Random's not bad intuition. So U is in tau 1. So U is a subset of X. That's all we know so far. Right?
Mm-hmm.
Can we write U any special way? So let U equal that. And let, I don't know what to call it, V. Maybe I'll write down here so that we don't have it on two lines. Let V equal X minus U. Or in other words, let V be U's complement. 3. observe that since x is finite, and we only made it smaller, what is v? It's all the elements in x that aren't in u. So we start with x, and we remove some elements. So how many elements can possibly be in v? A finite number. So observe that since x is finite, comma, and v can only be smaller than x, or the same size, or the same size. Smaller than x, comma, v is also finite. Okay. Long way to say that. So what did we just barely show? If v is finite, what is v? It's a complement of u. So u's complement is finite. So u is in the finite complement topology.
Yes. So U is in tau 2.
So perfect. Therefore, u is in tau 2, which means what did we just really show? We showed tau 1 is a subset of tau 2. That's what we show so far. We show pick any random thing you want in there, it's also in there. Now we need to do the inverse. We need to pick any random thing out there, show it's in there. And they show tau 2 is a subset of tau 1. This one's trivial. Sorry, I forgot to do my forward arrow, back arrow. I guess I didn't word it as an if and only if up there, that's why I didn't. But anyways, now, comma, let u be an arbitrary element in tau 2. What do I know about u? It has a finite complement, but we know even something simpler about u. It's a subset of x. All open sets are subsets of x. So I know that u is a subset of x, which tells me what?
U is in
U's in the power set of x. Because the power set is a set of all possible subsets. So I know that u is in tau 1. So we didn't need to sit here and do all this reasoning about, oh, we know it's a finite complement, so let's go think about its complement set, blah, blah. No. It's in a topology, so it's a subset, so it's in the discrete topology. If you grab an open set in any topology on a set, that open set will always be in the discrete topology, because the discrete topology is a set of all possible open sets. Right? Okay, so that gives us u's in tau 1. So what does that give us? That gives us that tau 2 is a subset of tau 1. 6. Therefore, tau 1 is equal to tau 2.
And that goes to show that the discrete topology is the same as the finite complement topology.
Yes, so if x is finite, then the discrete topology and the finite complement topology are one and the same. Now, what about in the case that it's not finite? If x is infinite? Then they're different. How are we going to argue that they're different?
I'm assuming from step 3.
So this is going to be its own proof. We won't go over basis today, but we'll just write it over here. So there goes our basis element. And we'll just do the proof here. Okay, so now we'll just pretend it's restart. 1. Let x be infinite, comma, let tau 1 be the,
Power set.
this was equal to the power set, so let tau 1 be the power set on x, comma, and tau 2 equal the finite complement topology. We'll just write it like that for sake of time. So we understand what these two topologies are, right? I need to show that they're not equal. How do I show that two sets aren't equal?
So that one subset, or one set is not a subset.
That works.
Don't you do
Even simpler though, I mean it's the same idea, but simpler way of saying it. If I can find one thing that's in here that's not in here, they're different sets. Right? So now I need to find one thing in here that's not in here. So 2, let little a be any random thing in big X. So we go to big X and we grab something out of there. Call it little a. I have no clue what it is. Then the set containing little a is for sure in the power set, right? That's for sure. Is it in the finite complement topology? Why not?
Because tau 1 is infinite and tau 2 is finite. So there's going to be numbers in tau 1 that aren't in tau 2.
Not quite. So then that is in tau 1, but V equal to the complement of this set. What's the complement of that set? It's going to be X minus A, right? How big is V? It's infinite. So the complement of little a is infinite. So little a doesn't have a finite complement. So V is a complement of little a, right? Is V finite or infinite? It's infinite. So A does not have a finite complement. So that gives me that V is infinite, which gives me that little a by itself is not in tau 2. Because its complement is infinite, not finite. So the finite complement topology is the same when your set is finite, different when your set is infinite. Which infinite set? Doesn't matter. Big XR could have been the naturals, could have been the reals, could have been the rationals, could have been the complex numbers, could have been the sets in the XY plane, set of points in the XY plane, doesn't matter. Make sense? Cool. So there we go. We're done with the first section of the book, topological spaces. Next week we'll talk about basis elements. Let me give you some intuition about basis elements really quick. That way when I give it to you again the second time, hopefully it sinks in. It's really tedious when we create a topology to write out every single open set. That's super annoying. Imagine for a second that we were creating a topological space, and our topological space was all the possible things that you could construct out of Lego. You know Lego blocks? So think about Lego blocks. And let's imagine that we had a topology where everything inside of the topology was all the possible things you can make out of Lego blocks. It's an infinite topology, right? Writing that out, no chance of doing it. But there's a finite number of types of Lego that we can use. And so maybe if I can list out all the types of Lego we can use, and then say, here's my topology. It's all these types, and then any way we can combine these types together. That's our topology. That's what a basis gives us. So it's really hard to take a topology by the horns and make sense out of it. So usually we talk about a basis, and then we reason about the basis elements rather than trying to reason about the whole topology in one go. That's what next week will be. We'll start talking about basis elements so that we have a better handle on how to deal with these infinite topologies. It's easy to deal with finite topologies, list out all the elements and think about it. We're talking about infinite topologies, a little bit hard to get a grasp on. Really helps to have a basis to talk about instead. So that's high level what basis is going to be. That's what we'll do next week. Any questions you want recorded before we're done? Cool. We'll call it there and see you guys next week.